Level 3 waves progress test. Question number 1, let's get into the multiple choice. A wave has a frequency of 50 Hertz. So frequency is 1 over time. It says what is the period? So we're looking for t, which is 1 over the frequency. We know the frequency is 50, and so I can simply go into my calculator, 1 divided by 50, and I get 0.02. So the answer has to be E. If the frequency of sound is doubled, the wavelength, well, we have V equals F lambda. We know that the V of the wave must stay the same. And so if frequency goes up, then the wavelength must go down by an equal amount. So to answer the question, if the frequency of sound is doubled, the wavelength halves and the speed of the sound remains unchanged. Okay, question 3. A place of zero displacement on a standing wave. Well, an antinode is when you have maximum displacement. A node is the correct answer because there's no amplitude. The amplitude is what you're measuring on a wave. So if you've got a sine wave, then this here is called your amplitude from center to peak. So it's not that one. The wave number is baby n, and so it's not that one. And a harmonic is definitely not a harmonic. So the correct answer is B. Question number 4, sound and air can best be described as which of the following types of waves? Longitudinal, transverse, maybe one of those two. Torsional is not a force in a rotation, so no. Electromagnetic, well, is sound part of, is it visible light, an X-ray, gamma ray? No. Is it polarized? Well, polarized is when we cut out a particular one of the three-dimensional parts of the electromagnetic spectrum, so it's not that. So it has to be either longitudinal or transverse. If we look at hyperphysics, for a transverse wave, it's when the displacement of the medium is perpendicular to the direction, so it travels this direction and it's going up and down. And so an example of that would be visible light. Where if we look at longitudinal, the displacement of the medium is parallel, so in the same direction. On the BBC Bite-Size website, we can see this. So there's the changes at 90 degrees to the movement. Where we're longitudinal, the change is in the same direction. And so this here is sound, this here is light. So the answer to our question must be A, longitudinal. Which station broadcasts with 3.27 meter radio waves? So we're looking for a frequency, and so then I use V equals F lambda, and I'm trying to find the frequency, and so it's going to be velocity divided by lambda. I think the hardest thing here is to figure out what the velocity, so they've said it's radio waves, and I know radio waves are part of the electromagnetic spectrum, and so I know that they must travel at the speed of light, 3 times 10 to the 8 meters per second. They've told me the wavelength is 3.27 meters, so then I can come over to my calculator and I go 3e8, which means 3 times 10 to the 8, and I divide it by the wavelength of 3.27 meters, and I get this massive number. Now, it says the answer should be somewhere in the megahertz. Now, I know that mega means times 10 to the 6, and so I'm going to divide by 1e6, and so then I should get an answer that looks the same. And so I do. I get 91.7 times 10 to the 6 hertz. So therefore, the answer must be A. A diffraction grating has 1,000 lines per centimetre. What is the distance between any two given lines? And so that is my n, but it's not quite right because it should be lines per millimetre, per metre. So if there's 1,000 lines in a centimetre, and then I times it by 100 to get that in a metre. And so I'm after the distance between any two slits, and so that's d, which is 1 divided by n, and so it's 1 divided by 100,000. So 1 divided by 1, and I get 1 times 10 to the minus 5. And so the answer must be C. The standing wave pattern diagram to the right is produced in a string fixed at both ends. The speed of the wave is 2 meters per second. What is the frequency of the standing wave? Well, I'm going to be using V equals F lambda, and I need to know which harmonic this is. And so I know it's the 4th harmonic, and I also know that there is one wave and a whole another wave, and so I know that there's 2 waves equals 1 meter, and so I know that the wavelength is half a meter. I could have also referred to my sheet that I've been given in class and see that it's the 4th harmonic, and that lambda equals 2L over 4, and so I could have done it that way as well and said that lambda equals 2L over 4, and so it's 2 times 1 divided by 4, and I would have again got 0.5 meters. as my wavelength. And so I'm after the frequency, and so I'm going to rearrange this to make this frequency equals v over lambda. I know the speed that was given to me in the question is 2, and I know the wavelength is 0.5. So 2 divided by a half is going to give me 4 Hertz. So I know the correct answer is D. Question 8. If the speed of sound in air is 340 meters per second, the length of the organ pipe open at both ends that can resonate at the fundamental frequency is 136 Hertz would be what? Well, if I was to draw that wave, it might look something like this in an open pipe. And so I know that lambda equals 2L, and I know that V equals F lambda, and I need to find out what my wavelength is, and so I'm going to rearrange this for lambda. So lambda equals V over F. I know the speed is 340. I know the frequency of the fundamental is 136 Hertz. And so I come over to my calculator and I go 340 divided by my 136. And that gives me a wavelength of 2.5 meters. Now I know that if it has a wavelength of 2.5 meters, then I can look at this and I say, well, L equals lambda over 2, and so it's 2.5 meters divided by 2 gives me 1.25 meters long. So the answer must be C. Question number 9. Two sources in phase and a distance d apart each emit a wave of wavelength lambda, and see this figure here that we're looking at. Which of the choices for the path difference delta L between L1 minus L2 will produce destructive interference? Okay, and so if we were to draw a circle with the center of the circle there, and I was to curve it around and make it would keep going around in a circle, then we can see that the wave must have travelled this extra distance here, which we normally call PD, or the path difference. When it is destructive, then we know that the path difference must equal half a wavelength. And so what is the answer? Well, it must be half a wavelength. If it was 2, then it would be constructive. X over L doesn't really make sense. None of the rest really makes sense. So D must be the correct answer. Question number 10. In an experiment to measure the wavelength of light using a double slit apparatus, it is found that the bright fringes are too close together to easily count them. To increase only the spacing between the bright fringes, one could, well, let's first look at the formula. We've got D sine theta equals n lambda, and we need to increase essentially angle. If we increase the angle, then we're increasing the spacing, and so we could have a laser that's going through a diffraction grating, and they're a certain distance apart. From there they're going onto a screen, which is a distance L away, and they might appear up here, which is a distance x from the center. And so we want to increase these x's, and the way we do that is by increasing angle. So we need angle to go up, and we can change the slit separation. And so n lambda is fixed, and so if angle goes up, then that means that d has to go down. So the answer must be D, decrease the separation between the slit, which is D. It can't be B, the slit width, because it's not about how wide a particular slit is, it's about what's the distance between given the slits. That's what our letter D is in our equation. Radio waves, infrared radiation, visible light, ultraviolet radiation, gamma radiation. For the 5 types of electromagnetic radiation listed above, which of the following correctly describes the way in which wavelength, frequency, and speed changes one goes from the left to the right? I know that gamma is high energy, so that means it is also high frequency. I know that radio waves are low energy, and so low frequency. And so this is high wavelength and low wavelength. And so going from left to right, the wavelength gets smaller, so this goes down, frequency goes up, speed is constant. So not the first one. Yes, B, the correct answer. Question 2, the noisy pipes. Eloise decides to fix a number of hollow pipes to the outside of her house. I call them wind chimes. These pipes are open at both ends, and so when we think of open at both ends, the first thing we should think of is that lambda equals 2L. And each resonates with a note of a particular frequency when the wind blows across them, and a pipe has a length of 1.22 meters. Sketch the fundamental, okay, this is the key word, the fundamental harmonic on the diagram to the right, and label the displacement nodes and antinodes. Something a little bit like that. It's a little bit wobbly, it should be perfectly in the middle. My picture's not really that great. The second bullet point, show the fundamental frequency of the standing wave is approximately 141 Hz. And so we've got V equals F lambda, and it is asking for the frequency. So if I rearrange this, it's going to be velocity over the wavelength. And I know up here that it's a warm day and the speed is 343 meters per second, and the wavelength is going to be twice the length. And so 343 divided by twice the length, and if they told me the length somewhere, yep, I've written it out, 1.22 meters, and we can come over to our calculator and go 343 and push equals, and I get 140.57 Hertz, which is basically the 141 Hertz they requested. That is worth a merit. Question B, on a cooler day, so that tells me that temperature has gone down, the same pipe is found to resonate at a frequency of 137 Hz. And so that tells me that the frequency has gone down. Eloise knows that the speed of sound has decreased, so we know that the velocity of sound has gone down, and that the pipe has shrunk, and so the L has gone down. Discuss how it is possible for these two changes to cause the observed change in resonant frequency. So we're talking about the frequency. You may wish to include calculations in your answer. Well, I know that the speed of sound is 331 meters per second plus 0.6 T, where T is temperature measured in degrees centigrade starting at 0. So if the temperature has gone down, so if temp has gone down, that means that the speed of sound must have gone down. Now how will that impact my frequency? Well, I know that V equals F lambda, and so if speed has gone down, so if V has gone down, and if I assume the same wavelength, because if we are talking about the same pipe above, then I know that lambda equals 2L. Now if the length of the pipe is fixed, then that means that the frequency must have also gone down. So if I was to put that into words, the speed of sound is dependent on temperature. If temperature decreased, then the speed of sound has also decreased. From V equals F lambda, if we temporarily ignore the change in length of the pipe, so then L is fixed, and so from lambda equals 2L, because we know it's the fundamental, wavelength is fixed. And so if lambda is fixed and V goes down, then that means that frequency must have also gone down. And so that will give you an achieved, maybe a merit. But we need to look at how the length would change. As temperature goes down, we would assume a contraction, so we would assume that length would go down. And so if length goes down from lambda equals 2L, if L goes down, that means that lambda goes down, and then from V equals F lambda, if lambda has gone down and the speed of sound is fixed, then that means that frequency has actually gone up. So let's put that into words. So when the pipe cools, it contracts, its length will decrease, so L will go down from lambda equals 2L, because we're still talking about the fundamental. If L goes down, the wavelength will also decrease. If the speed of the wave is constant, so we'll only look at the effect of the change in length, okay, then we'll find from V equals F lambda that if lambda goes down, V is fixed, F must actually go up. And so the question is, well, this one's saying frequency is going to go down, this one's saying frequency is going to go up. Well, which one's going to have the largest effect? Well, we can see that every degree change in temperature, there's a 0.6 change in speed. So speed's going to be a huge impact, where the change in the length of the pipe is going to be very little. So the net result is frequency is going to go down. So let's put that into words. So my final line, because the change in length is very small and the change in temperature is significant, the net result is a decrease in frequency. That is worth an excellence. Question C, Eloise finds that a short pipe that is closed at one end produces the same fundamental frequency as the long pipe that is opened at both ends. Okay, so we know from V equals F lambda that because the speed of sound is the same, and if the frequency is the same, that means the wavelength is the same. Okay, so explain the difference in the sounds that Eloise hears. In your answer, you should explain I, how pipes of different lengths can produce the same frequency, and double I, why Eloise notices a difference between the sounds. So I is worth a merit, and double I is worth an excellence. So let's have a look at this. So if we're to draw these two waves, we've got an open pipe wave, and we've got a closed pipe wave, and we can see both have the same wavelength. So we've got an antinode, we have a node. We can also see that if we were just to continue this wave up, then we would in fact have exactly the same wavelength, because this effective L length would be the same, and so we have the same wavelength even though one is in an open pipe and one is in a closed pipe. So let's begin to unpack this a little bit more. Remember our formula sheet that for an open pipe, that lambda equals 2L, and for a closed pipe, lambda equals 4L. And we know that because they have the same fundamental frequency, the same speed of sound, that they must have the same wavelength. And so if I call this length open and length closed, then I know that 2 length open equals 4 length closed, or that the length open is 2 length closed. And so I know that length open must be twice as long as length closed, which kind of makes sense because that's exactly what you're seeing here, that this is half the length. So in words, I could say something like the shorter closed pipe must be half the length of the open pipe, and we've just kind of shown that, and it kind of makes sense from our picture. Both pipes have an antinode on the open end down here, a node in the center on the closed end wall for the closed pipe, so there's the node on that one, and the open pipe also has an antinode at its second open end. What that really kind of means is that a quarter of a wave fits into the closed pipe and half a wave fits into an open pipe, and that's what they're after for I. So that was worth a merit. We haven't even touched a double I, which is worth an excellent. So why Eloise notices a difference between the sounds, even though they're producing the same fundamental frequency, that same fundamental wavelength, the same, the speed of sound is the same. Why are the notes different? The reason why the notes are different is because they're not just hearing the fundamental. If we look at an animation, all we're seeing here is the first harmonic. However, in reality, it's never just the first harmonic. It's always a superposition. It's always the adding together of more harmonics. So for a double-ended pipe, what we're really seeing is the first, second, and third, maybe the fourth, maybe the fifth. It gets very, very complicated. And so what do all those added up look like? Well, they look like the white wave. And the more harmonics we take off, the simpler that wave gets. And so we're always going to have the first harmonic. But there's always going to be a combination of the next. So that's fine when it's a open-ended pipe. But what about a closed pipe? Well, remember, for a closed pipe, that we can't actually have even harmonics. Even harmonics don't exist. So we can have the first one, the second one, the third one, the fourth one for open pipes, but we can only have the first and the third and the fifth. And so that's the reason why the sound sounds different, because the superposition of these different harmonics can't be the same as the superposition of these ones, because these ones will include even and odd, and these ones will only include the odd harmonics. So let's see if we can put that into words. The sound being played from the pipes will not only be their fundamental frequency, it'll be a combination of higher order harmonics. The sound we hear from the open pipe will be the superposition of both even and odd harmonics, giving a distinctly different sound to the closed pipe, which can only sound odd harmonics due to the need of a node at the closed end of the pipe. That there is worth an excellent. On a warm, windy day, okay, so warm telling us the speed of sound, windy meaning that there's some sort of vibrations happening across these pipes. Eloise finds that a note with a frequency of 282 Hz is produced by the 1.22 meter long pipe that is open at both ends. She blocks one end of a 0.61 meter pipe, expecting to hear the same note, but finds the note she hears has a completely different pitch. Okay, so that's saying that the frequency from the open does not equal the frequency from the closed. By calculating the wavelength of the 282 Hz wave, explain how the open pipe is making the sound, and discuss why in these very windy conditions. Okay, so they're trying to emphasize this idea of wind. A closed pipe of half the length of an open pipe does not produce a note with the same pitch, although we just figured out in question C that that should be the case. Okay, so let's use our formula. We've got V equals F lambda. It's asking us to find the wavelength, so lambda equals velocity over frequency. Over the page it says the velocity is 343 meters per second on a windy day, and they've told us that it's 282 Hz. So we can work out the frequency is 343 divided by 282, which gives us a wavelength of 1.22 meters, which just happens to be the same wavelength as that of the pipe. So that tells us that a whole wavelength is going to fit inside this pipe. Something very, very roughly like that. And so what does that tell me? Well, that tells me that this is the second harmonic. If that's the second harmonic, And then we think about it, well, can we actually have a second harmonic for a closed pipe? No, we can't have a second harmonic for the closed pipe. And so we can't fit a 1.22 meter wavelength inside this, because we can only have the first and the third and the fifth harmonic on the closed pipe. And essentially that is the answer. So in words, the 1.22 meter long open pipe is producing the second harmonic. The first harmonic must be missing due to the large vibrations occurring at the end of the pipe due to the very windy conditions they keep emphasizing. The closed pipe can't create a second order harmonic, it can only make odd harmonics, so it's impossible in the absence of that first harmonic in that pipe to hear the same pitch even when that length is exactly half. We could go further and say, well, for a closed pipe, lambda equals 4L, or lambda equals 4L over 3, and so on. And we could check this, and so we could say, well, if it was 4L, lambda equals 4 times 0.61, which it can't be that one. And we can go lambda equals 4 times 0.61 divided by 3. Well, this could be close. It might actually be worth checking, times 0.61. So that lambda is 0.81 meters. Again, is not the 1.22, so it is impossible. But if you wanted to show further working, then you could add that, but I don't think it's that necessary. So for this answer, we're looking at an excellence. Question 3, dodgy phone reception. Sarah is checking her cell phone reception on the ferry. On the car deck of the ferry, there's a series of windows in the metal wall. Sarah walks along the deck, monitoring her signal. She notices a pattern of strong and weak reception. Sarah thinks the pattern has formed because microwaves from the transmitter have entered the ferry through the window gaps in the metal wall and formed an interference pattern. The diagram below shows the situation. Is Sarah's theory plausible? In your answer, explain how microwaves form this pattern and what determines the positions of strong and weak reception, and how the number of windows in the wall affects the contrast between strong and weak signals in the pattern, and how it affects the width of the strong and weak signals. So I is worth an excellence, and double I is also worth an excellence. So there's 2 excellence credits up for grabs here. So essentially, what is happening? Well, could the microwaves come through here and after every slit create essentially a point source of waves, and could these essentially interfere? Well, I think that is a feasible option. Why would there be strong and weak areas? Well, there's that whole idea of constructive and destructive interference. It's getting very messy now. If you're wanting to really explain it, you have to talk about path difference and phase. So let's have a look at a wordy answer. Yes, Sarah's theory is plausible. Microwaves, like light, are part of the electromagnetic spectrum and diffract around barriers a similar size to the wavelength of the wave. And so microwaves and the size of the waves are roughly in the same order, and so it is possible. So the microwaves act as individual point sources, all leaving in phase as they pass through the window slit. So as the waves come out, they're more or less in phase, and so they can interact with each other. When the waves constructively interfere, i.e. have a path difference of n lambda, so they're 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths difference, there's a strong signal. So they have, they're in phase essentially. When they destructively interfere, like they have a half wavelength for 3 over 2 or 5 over 2 path difference, or 180 degrees out of phase, then that is a position of poor signal or weak reception. So that answer there is worth an excellence. When we look at double I, how does the number of windows affect? So if we put more windows, so let's think this through. If we put more windows, what's going to happen to the spacing of D? So if we look up here, we have a spacing in between the windows, which is D. And so if we put more windows, D is going to get smaller. Okay, now if D gets smaller, well, let's have a think about what that happens to our equation. So we've got D sine theta equals n lambda. Does the wavelength change? No. Does the order that you're looking at, so from the first bit? No. So n lambda is constant. And so that means that if D goes down, that means that the sine of the angle has to go up. So if the sine of the angle goes up, what does that really tell us? Well, so if D goes down, sine of angle goes up, so angle goes up. And so if there's an angle, so you're talking about the waves coming through here, and now you're saying that that angle is bigger, you're essentially saying the spacings between a bit of strong good interference and another bit of constructive interference and another bit of constructive interference, those spacings are going to get bigger, is essentially what you're saying. And because you're adding more windows, you're adding more slits, they're going to have to become a lot more defined. So these are going to be really strong, and then it's basically going to be absolutely no signal, and then really strong, where you'd had a bit more of a gradient before. So let's see if we can put that into words. So in words, the more windows means the spacing between each window d decreases from d sine theta equals n lambda. If d goes down and n lambda is fixed, the angle must increase, causing the positions of constructive interference of the strong signal to be more spread out. Also, because of having more sources of diffraction, the positions of strong interference are now narrower. An answer like that is worth an excellence. The wall of the window is 5.42 meters away from the line along which Sarah is walking, and the distance between the window gap is 0.93 meters. The distance between points of strong reception is 53.4 centimeters. Well, first off, let's change that into meters, 0.534 meters, and positions between strong, so that's that distance there, which is what we'd call x. Now, the first thing you need to say is L much greater than D. So D is 0.93 meters, and this is 5 meters, so it's 5 times bigger, which is not much bigger. So this is not true. And because that's not true, you can't use the formula n lambda equals dx over L. Okay, you're not allowed to use it because this rule, which governs if you can use it, is L much bigger than D, is not true, so you can't use that equation. So what you need to do is you need to say, well, how far, or what is this angle here? Okay, so you know that distance there is 0.534 meters. You know that's 5.24 meters, and so you can use tan. You know the tan of the angle is opposite over adjacent. You're looking for the angle, so it's going to be arc tan minus 1 of opposite, which is 0.534, divided by the adjacent, which is 5.42 meters. We chucked it into a calculator, making sure that my calculator is in degrees. Shift tan of 0.534 divided by 5.42 gives me an angle of 5.6 degrees. I'm going to store that in my calculator as alpha A, so then I don't have any rounding errors. So has this really helped me so far? What am I trying to work out? Well, I've worked out the wavelength, and then I can work out the frequency from that. And so I've got d sine theta equals n lambda. Because I'm talking about the first one, this is the first strong one, so this is our n equals 0, and so this next one is n equals 1. I know that is 1. The wavelength is what I'm trying to figure out. I know d, the distance between the slits, which is 0.93, and so now I can solve for lambda. So lambda equals d, 0.93 times the sine of 5.6 degrees divided by 1. Okay, so I don't even need to divide by 1, and so that's my n, and so I can go 0.93 times the sine of alpha A, which is the angle I've just worked up there, so that I can't get that wrong, so 0.0912 meters is my wavelength, and so it asks for a frequency, and so I know that V equals F lambda. I know that microwaves travel at the speed of light, and so frequency equals V over lambda, which is 3 times 10 to the 8 divided by 0.0912. So 3e8, and you should use the exp button. You shouldn't go times 10 to the power of. It's just stupid, right? The exp button means times 10, and divide that by shift answer. Notice how I haven't typed in any numbers again. We should be doing that by the time we're in year 13. I've got this massive number that's too hard to write down, and so if I count how many digits, 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. So I'm going to divide by 1e9 to make sure I counted right, and I did, and so the answer is going to be 3.289. Wow, it's not going to be, is it? times 10 to the power of 9 hertz. And so if I was to write that more correctly, it'd be 3.29 times 10 to the 9 hertz. That first answer is a little bit rubbish, because I haven't rounded it right. So that there is the correct answer, which is worth an excellence. If you used the formula up here without realizing that L wasn't much bigger than D, you basically got the right answer, but you only got a merit for it. Well done, you've completed the test. Hopefully we've learnt something. God bless.